Problem 11.49. The slider block A moves to the left with a constant velocity of 6 meters per second. Determine the velocity of the block B, the velocity of portion D of the cable, and the relative velocity of portion C of the cable in respect to portion D. Okay, so let's start with what we know. We know that this guy is moving. It's too thick. And this guy is moving to the left with a constant velocity of 6 meters per second. Okay, we also see that we have B there, and B is attached, they are attached by pulleys. So if A is moving to the left, then that means that this is pulling this rope here, which is pulling on this rope, which is pulling on this rope, so that means that B is going upwards. Okay, so with that in mind, we can go ahead and actually place our systems to have an idea of what we're going to do. What I can do is I can place a axis here, and I'm going to do X is going to be this distance here from this system that I just created to the block A. That's my vector XA. Actually, I'm going to make this a vector. And for B, I'm going to take the same center there, and I'm going to make a Y vector, YB, I'll call it YB, which leaves from that axis I just created right on the pulley and goes down. Well, note that this part of the pulley here is kind of useless for our analysis, because whatever happens, if this guy goes up and this guy goes down, it's always going to be the same length. This distance here is always going to be the same, regardless of what happens to B. Obviously, if we had something like this, C and D here, like they were asking, they don't have to take into account. But for this top part, that's not the case. What else do we know from pulley? Well, these ropes, they're not stretchable or anything like that. So whatever the length of the rope, all has to be the same. So if I sum this portion here with this portion here, with this portion here, and this portion here like that, all that has to be a constant, because it's not going to change, because the rope's not going to change, right? So that means that if I do XA, that is my vector, plus 1, 2, 3, plus 3 times, I can get rid of this, plus 3 times YB, I'm going to have a constant. Well, let's just do a little extra. There's this extra bit here, okay? And I can call that whatever, but this is not changing. Like I said, the length of this guy is always going to be the same. So let's say this is, I don't know, 2 meters. Okay? So I'll put like 2 meters here, and that always going to be the same. Always going to be constant, right? But because 2 is a constant, if I remove it, this is still true, right? That guy is still true, but this is still a constant. Okay, so 3 times YB plus XA is a constant. That's what I'm saying in this equation here. The rope is not going to change length. What else? If I take create another vector, let me zoom in. If I create another vector, which is from my system to C, so it'll be a vector like this, and I'll call that YC, then I can create another equation relating the distance of the rope from here to here. Okay, that's also going to be a constant. In other words, what was my XA? So XA plus YC also has to be a constant. Different constant, obviously, because this is going to be greater than this, but that's not what I'm interested in. Because I'm interested in having those equations set up so they can find the velocity equations. And then finally, we're also interested in point D. And point D, let's change colors for point D. Let's go ahead and grab a purple. So same thing. I'm going to create a vector that's going to leave from the same place I've created the one for B, but I'm going to make it going all the way to D. And that's going to be my vector YD. And once again, I can create a constant equation for it. And I can do, there's a couple of options. We can do this here as a constant. That's an option. Another option is doing this here as a constant. So then we involve b again, and I'm going to choose that one. So if I take my vector y d and then sum up my vector y b, that also has to be a constant. Okay, and the same thing on this one applies as the green one that I drew before. We could have put +2 for that extra bit there, but we don't have to, right? Because the 2, this is also true. Okay, and you see that if you want to do that, if you want to add that 2 there, or whatever number you want to add for the extra bits, you can. It's just going to be, it's not going to change our analysis anyway. But the interesting thing of doing this is that once you have this system of equations set up, okay, now we can derive all of this. Because if we derive these guys here, they're all positions, right? All vectors that measure the position of the things in our system, and we derive that in respect to time, we're going to get the velocities. Right? So if I derive this in respect to time, we're going to get velocity of A plus 3 times velocity of B has to be what? Has to be 0, right? Because the derivative of a constant is 0. Likewise, the velocity of A plus the velocity of C has to be 0. And the velocity of D plus the velocity of B has to be 0. And this is, some of this gives us some insight, but some of this are just very, very intuitive. Like these ones, for instance, VA equals minus VC. So what is that saying? That's saying that if my A is increasing, that is, if my A is going that way, then my Y is going to be decreasing, right? It's going to be going this way, which is very intuitive, right? So if my A is going to the left, my point C is going to go upwards, right? Not downwards. Note that we made downwards positive here, and we made leftwards positive. Likewise, VD and VB, right? So if my YB is increasing, then my YD has to be decreasing, vice versa. And this is what this one is saying here. VD has to be minus VB. And finally, this one, which is probably the most important one, is the one that's related, that the velocity of A is three times greater than the velocity of B. Because for B to move 1 centimeter upwards, it has to move, these 3 ropes have to move the 0.3 centimeters. Whereas in A, if this one will move 1 centimeter leftwards, then only this rope here has to move 1 centimeter leftwards. Cool. Now we can answer the questions. What were the questions? I forget. A, what's the velocity of block B? Okay, so that's very straightforward. If the velocity of A is 6, so we can use this straight off. 6 equals 3 times, minus plus VB equals 0. So therefore, VB equals minus 2 meters per second. Right? So minus 2 meters per second means that this guy is moving upwards. Right? So this is moving upwards. So if A is moving to the left, B is moving upwards. And that is very, very intuitive when we look at the drawing. We might get rid of some of these things in the drawings to make our drawing less polluted. Okay, that's a bit better. What else? Next part of the question is asking us, what is the velocity of portion D of the cable? So portion D. So D is just negative B, right? So therefore, we can zoom in here. So D is just negative B, so that's just going to be 2 meters per second. So that's moving downwards. Once again, that should be fairly intuitive. If A is moving leftwards, then D is being, this rope is pulling this way, which is going to be pulling everything this way. It's going to be pulling this way, which is going to be pulling this way. So that means that RD is going downwards, which is our positive direction. So that is indeed intuitive. And finally, what is the relative velocity of portion C in respect to portion D? So let's look at these guys here. What is the relative velocity of C in respect to D? What is happening with them? Let's actually look. What is happening with them? We know that D is going this way, right? And we know, just by looking at the drawing, we can see that C is going this way. We can also solve for VC if we wanted to. So if we want to find what is the velocity of C in respect to D, know that the velocity of C if D was standing still, we just find the velocity in C and that's it. But D is going away from C, so from C's perspective, it looks like it's going actually as faster than it really is, right, relative to our perspective here. So what we need to do is we just need to get the velocity of C, and then let's do velocity of C minus velocity of D, right? So velocity of C, we've had it from the start here. Velocity of C is therefore VC equals negative 6 meters per second, right? So just negative of what A is. And if I want to do, let's get a different color. Let's go with the purple one. So if I want to know what's the velocity of C in respect to D, that would just be the velocity of C minus the velocity of D. We have everything we need. The velocity of C is minus 6 meters per second. And the velocity of D is 2, so it's minus 2 meters per second. So that is negative 8 meters per second. So from C's perspective, it's moving at 8 meters per second upwards in relationship to D, right? From our perspective that we're standing still, it's just moving 6 meters per second upwards, right?